more minute, we'll figure out what the matrix product AX is. So this is the matrix A, that's the vector X. They're also on the board. We just want you to enter in what is A times X. And there's an example of what your input format should sort of look like. That's this format here. If it's a vector with two inputs, just input them separated by a comma. So x plus 7, x plus y is x plus 7, comma, x plus y. And most people are in already, so that handful of people who are left. Now when you finish this, you can jump into part 2 of the question. Part 1, and we're just going to be going through the parts, sort of one by one. Okay, time's up. Let's see what people think. So, when there's quotes, you don't have to write the actual quotes. This is the correct answer, minus the quotes. So I think a lot of people are getting the right answer here. It's x plus 2y, 3x plus 3y. And the rule for matrix multiplication is you sort of go, people like to think of it as going row by column. So you go along the rows of A, and then you go along the column of the vector on the right. So you go 1, 2 with x, y. So that's like the 1. My left hand is going along 1, 2. And my right hand is going along x, y. So the first row is x times 1 plus y times 2. So x plus 2y. And the second thing is 3x plus 3y. So the vector you get is this. 1, 2, 3, 3 times x, y. So row by column. That's how I got these two things. So you should have seen this before in your web work. If not, you're going to be using it over and over again, so you're definitely going to have to learn this. It seems like a bit of a weird thing when you first see it, but we're going to see today and going forward why it's defined this way. Why do we do this funny multiplication? You'll see as we get going why that is. Okay, so the next part of the question asks you for write down the system of equations that corresponds to the matrix equation AX equals B. So I'll give you 30 or so seconds to do that. It should be fairly quick, and then we'll write down the solution on the board. So take a stab at that for 30 seconds. A system of equations that corresponds to AX equals B. Okay, so that should hopefully be enough time. Who wants to tell me what is the system of equations they got for AX equals B? Yeah?
X plus 2y is equal to -2, and 3x plus 3y is equal to -1.
What was the second one?
3x plus 3y is equal to -1.
Yeah, very good. So this is AX. So if you put AX equals B, you put the vector B here. So I'm doing a little cheat here, reusing the stuff I already have on the board. So we know that this is AX. So this thing is AX. We're doing AX equals B. B is the vector -2, 1. So the vector equation AX equals B is this equals this. And every vector equation that has two components gives you two equations. Each component of a vector thing gives you a different equation. So this is sort of like something we're super familiar with from all our web work before, solving linear systems. Now we're going to see how it connects to these matrix type equations. Before we go any further, here is a quick thing for you guys to keep your eyes peeled for, which is here we have x plus 2y. And my question is x plus 2y a dot product? I'll give you just 1 minute to think about this. This will be a fast one. Alright, let's see what you guys think. Is it a dot product? Everyone says, but of course, it's like a great coupon ad. Why is it a dot product? It doesn't look like a dot product to me, but everyone said it is. Why is it a dot product? Yeah?
Well, we can take x, y, and 1, 2.
Yeah, so actually, you can write x plus 2y. You can definitely write that as the dot product 1, 2 times x, y, or dot product x and y. So of course you can do that. You can do all sorts of crazy other things that are dot product that work out to this. In this problem though, I think this 1, 2, x, y thing is actually really natural because remember, how did we get the equation x plus 2y? It came from the first row of A, 1, 2, with the vector x, y. So really these equations, they are linear equations, but they came from really doing dot products. And so this is one of the ways to think about matrix multiplication. There's going to be two ways. Matrix multiplication. So the first way is to think in terms of dot products. So if you have the rows, you call the rows of the matrix A row 1, row 2. You take the vector x, you multiply a matrix that has two rows, row 1 and row 2 by x, you get the components are the dot products. So they're row 1, dot product of x, and row 2, dot product of x. So these two things you can think of as dot products. That's where they came from. You can also think of them as linear equations. Okay, good. The next two parts of the question are asking you to sort of think about interpretations of things. So it's saying, if x naught y naught is a solution, explain what x naught and y naught mean in terms of linear combinations. So sort of, it's kind of like, how would you think about this if you wanted to think about linear combinations? So I'm going to ask you guys to fill in a blank here on what you think the coefficients are. And I kind of set it up a little bit so that it leads you in sort of a specific direction. It says, if you think about ax equals b in terms of linear combinations, then if x naught y naught is a solution, then x naught and y naught are the coefficients for blank. So think about what could x naught and y naught be the coefficients for. Okay, so you have about 2 minutes to work on that. I'll come around if there's any questions. But in the meantime, start thinking about how would you think about it in terms of linear combinations. Okay, so there's about 10 seconds left. Maybe the answer is, I have no way to think about this as coefficients. That's a valid answer if you have no idea. This is kind of a loosey-goosey question about how you think about something. Okay, let's see what did people say. A plane, ax equals b, Someone wrote in a vector, 4/3 minus 5/3, I don't know what that is. AB, column in the matrix. No, no, no. The larger matrix dot product. So a lot of people I think are a little unsure about these things. Let's, oh, this is a nice long one. The column vectors of A so that they could combine to form B. Okay, that's a pretty well thought out one. Vector B. Some people are writing, oh, 1, 2, and 3, 3. So these are two specific vectors, I guess, 1, 2, and 3, 3. And this person is saying that x naught, y naught can be the coefficients of those. Okay. Oh, same answer over here. 1, 1, 3, and 2, 2. 1, 3, and 2, 3. Oh, these are different. This person wrote 1, 2, and 3, 3. This person wrote 1, 3, and 2, 3. So at least one of them is wrong. Possibly both of them. 1, 3, and 2, 3. Okay, another vote for 1, 3, and 2, 3. Another vote for 1, 3, and 2, 3 over here. Okay, a few votes for that one. So let's think. I think something, either this one or this one is true. Let's think about which and we'll revote. So I'll give you guys another minute to think about that. And feel free to discuss with your neighbor what you think is going on here. What's the right sort of interpretation? No, just this possibility. Yeah, well, I didn't know I was going to be recording it until at 12:30 when I was supposed to start. They were like, classes are canceled starting at 4. That's when I decided. So it's like, I'm not sure yet. Yeah, we'll Okay, let's think. Maybe that wasn't enough time. Who needs more time to think about it? Who's ready? Who's just tired? Okay. Good to know. Good to know. Let's see what you guys say. I guess I'll do the word cloud, and we'll compare in the word cloud. We'll compare 1, 3, 2, 3 to the other answer. So it looks like in the word cloud, 1, 3, 2, 3 over here in the corner. That it looks bigger to me. There's another 1, 3, 2, 3 over here with round brackets. 1, 3, and 2, 3 up here. So a lot of people are saying 1, 3, and 2, 3. And I think that's a totally legit answer. So that is the correct answer. I'm going to write them as column vectors. So 1, 3, and 2, 3. This is x naught and y naught. So this is, we're saying the matrix equation A times x naught y naught equals B is the same as saying the coefficients in front of 1, 3, and 2, 3 are x naught and y naught. And I guess the whole point is that this is going to equal B is minus 2, 1. So we're saying the matrix equation A times x equals B is the same as this linear combination. And that's exactly right, so you can check from what we have earlier, x plus 2y, here it's x naught plus 2y, if you could do the first component. Everything seems to match up. How did you guys get 1, 3, and 2, 3? Where did those come from? Yeah?
If you just look at the system of equations over there, you can change it to x and 3x, two vectors x and 3x plus 2y and 3y, and then just take x and y.
So you can sort of, you look at this thing and you sort of think of, well, the first thing you can factor an x out of the first thing, and the second thing you can sort of factor a y out of the second thing, and then so if you finagle a little bit, you can get here. I totally agree with that. I think there's an easier way to see it. It's a little higher up. Does someone else see? Someone said it in the first row. It's the columns of A. So these vectors 1, 3, and 2, 3, those were the columns of A. 1, 3, and 2, 3. So actually this is a whole other way of thinking about matrix multiplication. When you're doing matrix multiplication, what you're really doing is linear combinations of the columns of A. So I wrote down one interpretation of matrix multiplication up there in terms of rows. If you do rows, you're thinking of dot products. If you do columns, you're thinking of linear combinations. So let me write down. Let me write this down. So this is the rows. This is columns. So if you write them, the vectors, which are the columns of the matrix A, there's two columns, C1 and C2. In our example, they are 1, 3, and 2, 3. And if you do this multiplication, you get a linear combination of the entries, of the columns. So here, instead of writing x and y for the vector x, I wrote x1 and x2, because that way it works nicely. You got x1 with c1 and x2 with c2. So here x1 and x2 are the components of the vector x. c1 and c2 are the two vectors which make up A. So those are the two ways to think of matrix multiplication. It's going to be a big topic going forward, and just like a lot of things in this class, sometimes it's better to think of it this way. It's like more intuitive, easier for your brain. Sometimes it's better this way, and that's why it's really good to know both. You can always double check a problem by thinking about it more than one way. Okay, last question in this problem, part 4. Part 4 says, explain what x0 and y0 mean in terms of intersecting lines. So I'll give you guys a stab at this one. What do x0 and y0, a solution to the system, mean in terms of intersecting lines? And I have another fill in the blank for you. When thinking about ax equals b as the intersection of two lines, the two lines that are being intersected can be written in normal form in terms of blank. So not only do I want to do intersecting lines, I want to do intersecting lines in normal form. So you maybe have to remember what normal form is. That's the question. I'll give you guys a couple minutes to think. How does this relate to normal forms of intersecting lines?
Or regular.
Okay, there's 15 seconds left. So if you're totally confused about normal forms of lines, what does that do to this question? You can answer, I don't know, or I'm not seeing it. Something like that. That's a fair answer when I only give you 2 minutes to think about something. Okay, let's see what people think. I don't know. Oh, sad face. I thought it was a smiley face at first. Okay. I don't know is a smiley face because it means now you can learn something, right? Nothing's better than that. Okay. Think of the two equations as two x, y lines and they intersect at x0, y0. So that's right. So you can think of these two things as lines. And what we're looking for, when you have a system of two equations, you're looking for the intersection of the lines. So we already said we're doing these two things. We're looking for the intersection of these two. If x0, y0 is a solution, it means that it's the intersection of these two lines. So the only little ingredient that is missing from that answer is what it has to do with normal form. So let's see if somebody later on can answer this normal form thing. Normal form. Dot product. Normal form does have something to do with dot product. Okay. Someone wrote 1, 2, 3, 3. 1, 2, 3, 3. What is 1, 2, 3, 3? Okay. Okay, here's a good one. Dot product of the two vectors 1, 3, and 2, 3. So this person wrote 1, 3, 2, 3. This person wrote, let's go back up to here, 1, 2, 3, 3. So we got answers both ways again. just like before. And I'm going to tell you guys it's got something to do with one of those two sets. So you guys got to decide which. Does it have something to do with 1, 2, 3, 3? Or does it have something to do with, what was the other one? 1, 3, 2, 3. So take another minute, talk to your neighbor, see if you can remember what normal forms of lines are. Alright, let's see if there's any more luck with the hints. Let's jump straight to the word cloud. People are saying 1, 2, 3, 3. 1, 2, 3, 3 is the most popular answer in the word cloud. And indeed, this is a line. The normal form of this line, you would write it like this. You would write 1, 2, dot, x, y is equal to minus 2. That's a normal form of line. That's one way you can tell me a line. I'm thinking of the line that is perpendicular to the vector 1, 2, and it's sort of, in some sense, it's at distance minus 2 away from it. So that's something, if you remember the equal sign over here, it tells you if you're at the origin or not. If it was a 0, it would be a line through the origin. This sort of tells you the shift of the line from the origin. So it's perpendicular to 1, 2. It's shifted enough to make this minus 2. What about this one? This one is the dot product 3, 3 with x, y. So the normal forms of these lines are given by 1, 2, and 3, 3. Where can you find 1, 2, and 3, 3 on the board other than this little spot? From the rows of A. So if you think about it in terms of linear combinations, in the last problem, we were using the columns of A. If you think about it as lines, these dot products in these rows, the row 1 dot x, row 2 dot x, these you can think of as the normal form of lines. So those are two ways to think of matrix multiplication, either as columns or as rows, and there's sort of two different interpretations. And they kind of, sometimes if you want to think of intersecting lines, you should think of the rows. If you want to think of in linear combinations, you should think of the columns. Okay, we're going to get more practice with that as we go on today. So the next question is exactly about this kind of thing. We got 3 vectors in this question, u, v, and w. And the question is, how would you figure out if u, v, and w are independent? How would you figure it out? So start thinking about how you do that up, set up anything you want to set up. And then we're going to try to rephrase what we did in terms of matrix multiplication.
Oh, and the next part is going to be rephrased in terms of matrix multiplication. Yes. Did you only want to finish that? Yeah, you want to do a little cool and see our
So the first part of this question, thinking about linear independence of 3 vectors, this should be something that is your bread and butter. This is something you've practiced a lot. You should have known it for the midterm. What do you do if you want to find out if 3 vectors are independent? This would have been a good midterm question. We should have put it on there, and now you would all know. Yeah?
Just check for every vector if it's in the span of the other 2 vectors. At least that's the geometric interpretation.
Ah, you check if if the span of those three vectors is everything. Is that what you're saying?
Oh no, you take like U and V and check if W is in that span. And then do that for all.
Okay, so this is the geometric version. You check is W in the span of U and V. So this is an in question mark, right? We don't know if it is or not. We're going to check. So how would you check? Is W in the span of U and V or not? Hard to say by looking, right?
Yeah.
Another thing, I think you've forgotten two things on the board. Even if W is in the span of U and V, we got to check the other two combinations. So this one, it's hard to sort of look at. And then also, we're going to have to do it 2 more times. So this way, I think you can make this work. It's a little bit tougher. Yeah?
I would just create an augmented matrix with 0, 0, 0 on one side, so what the coefficients are.
Okay, so you're going to do an augmented matrix. So that's 1, 2, 3, 4, 5, 6, and 7, 8, 9 with 0, 0, 0. So what is that doing?
And put in reduced row echelon form.
Then you reduce row echelon form it.
And then if the coefficients are all 0, then you know that it's independent.
If the coefficients are all 0, if they're all 0, what happens?
They're independent.
Then independent. So this thing up here, this was the geometric version of independence. This is doing taking an augmented matrix, doing reduced row echelon form. What kind of thing we're doing here? This is a linear system in disguise, right? Every time you're doing an augmented matrix, you're really talking about a linear system. And the system here is 1 times x plus 4 times y plus 7 times z equals 0. That's the first line. 2 times x plus 5 times y plus 8 times z equals 0. And 3 times x plus 6 times y plus 9 times z equals 0. So these two things represent the same thing. The main reason we like to do augmented matrices instead of writing out equations is because we're lazy. We don't like to write all the pluses. We don't like to write the x, y, z. It's just faster to write it this way. But these two things represent the same thing. So every time you're doing augmented matrix stuff, you're really doing linear system stuff. And saying that if all the coefficients are 0, then they're independent, that's exactly the algebraic version of linear independence. So that's saying the only coefficients for a linear combination to be 0 are when all the coefficients are 0. So another way you can write this is as the vector equation, x times 1, 2, 3 plus y times 4, 5, 6 plus z times 7, 8, 9. So these things are the same as linear combinations of the columns. Okay, part 2 is what we really want to do today, which is how would you do it in terms of matrix multiplication? Matrix multiplication is what we saw in the first question. What does all this have to do with matrix multiplication? That's the question for you, and I've phrased it as an open-ended question here. Make a statement that is equivalent to the statement U, V, W are linearly independent using matrix vector multiplication AX. And so in your answer, just write AX to mean matrix A times X. What does it mean in terms of the matrix A whose columns are U, V, W? That's the question. It's open-ended, so lots of possible answers here. I'll add some time and give you a couple minutes to think about it. Okay, 15 seconds left. You guys are very quiet today. Stony silence all over the room. What does any of this have to do with the product AX? Let's see what you guys think. Okay, the first one that is a little bit longer. The only solution to AX equals 0 is when x is the 0 vector. That's very similar to what was written here. If the coefficients are all 0, I guess what we meant when we said if the coefficients are all 0, we meant the only solution is when the coefficients are all 0. You might have even said that. I wrote it down wrong. Is that what you meant? When we wrote down if the coefficients are all 0.
Yeah.
Yeah, so we meant if the only solution is the coefficients are all 0. Let's add that in. Yes, so let's add the words the only solution. Is when, I guess. Okay, well, the rest we can figure out. So this is saying the same thing, except instead of this system of equations, or this reduced for echelon form, they're doing AX. All right, let's see what other people have written. There's only one solution to AX. So I guess they probably mean there's only one solution to AX equals 0. You can't have the solution to AX. AX is some vector, but AX equals 0, you can have a solution. AX equals 0 only when x is the 0 vector. AX has only one solution. So, lots of people have written the same kind of thing. Let's see in the word cloud if it made it there. The word only, that's a big one. AX equals 0, that's good. And in fact, what we said earlier is that you can think of matrix multiplication as linear combinations of the column vectors. So AX equals 0 is the same as the linear combination of the rows of A being equal to 0. And the coefficients in front of the rows exactly come from the vector x. So this system of equations that we have here is the same as the linear combination of columns of A. So let me write that down. Matrix A times vector x is the same as the linear combination of the columns of A. So saying we're looking for a solution where this equals 0 is the same as saying we're looking for coefficients to make this system 0. That's the same as what we said earlier. So that's the connection. Any questions or comments about this one? So again, same kind of thing as in the first question. The point is that we're going to shift from thinking from equations to thinking in terms of matrices. And some of it is going to be the same, and there's going to be new things that are going to be added on that you can do with matrices that you can't do with equations, or at least that are more complicated to do with equations. But all the old stuff is going to carry forward into this matrix language. Okay. In the interest of time here, this next question, question 35, I think is one that you guys can do. It's not too complicated. It's exactly kind of dealing with what are the cases for this doing a solution to this kind of system. So we're going to leave this one for you guys to do at home as homework. And we're going to jump straight into question 36. Here's question 36. This one is about planes and matrices. How do planes and matrices interact? So take a second, read the question, start working on parts 1, 2, and 3. And we'll take it up in a few minutes. It looks like people are waiting for an answer to put in. I'll give you guys a break because you're tired today, as we discussed. But the first part should be easy. How many rows does it have? How many rows does M have? So hopefully you've read the question, you know what M is. Otherwise, you're going to be confused. Okay, how many rows does M have? 77% of people think it's 3, 21% of people think it's 2, a couple of people think it's 1. Maybe that button was closer to their finger than 2 or 3, and they didn't feel like thinking today, so shame on them. 2 and 3 are the relevant things in this problem, right? 2 and 3, there's R2 and R3, they're both in the problem. It's going to be one of them. It's going to be either 2 or 3. They're both good answers. Remember, R is a vector in R2, so R is in R2. So you can think of R, this vector R, as a 2 by 1 vector. A 2 by 1 vector. Things in P, so elements of P, those are in R3. The plane lives in R3. So the thing that is in P is a 3 by 1 vector. It's got 3 rows and 1 column. It's a column vector with 3 entries. So M is a matrix. It inputs 2 by 1 things and it outputs 3 by 1 things. And when you think of matrix multiplication, you guys remember how the dimensions for matrix multiplication work? So this is another thing that was on your web work. Okay, so I think this is a good hint that should give you the answer to the question. So I'm going to do 30 more seconds on top hat, and then we should have everybody, 100% of people, in either 2 or 3, according to what is the right answer. Let's do this one. That's a roll.
That's the roll, right? But the number of rows.
Okay, I'm going to stop this at 30 seconds, so you have 5 seconds left to sort of change your mind, if you want to change your mind. Okay, here we go. 8. 8 is not correct. Now we're up to 82% of people in 3. 3 is the right answer. And in fact, you can figure out exactly what the dimensions of M are from what I'm doing here. This is a 3 by 1, this is a 2 by 1. The rule for matrix multiplication is that, first of all, the number of rows of R has to match the number of columns of M. So this is going to be a something by 2 matrix. These two numbers always have to be the same. So this is the number of rows times the number of columns of each of these things, rows and columns. And the rule is that the number of rows has to match the number of columns of the other guy. So the number of columns of M has to match the number of rows of M. That's because when you do matrix multiplication, you go row by column. So you got to have the same number of things. Another way to think about that is, remember the dot products here, you do the dot product of the rows with X, so the number of rows has to be the same as the length of X. I said that backwards. So each row has to be the length of X, otherwise the dot products R1.x, R2.x don't make sense. So that has to be 2. This number is going to be the same as the number over here. So when you do matrix multiplication, these two kind of smush together, and you're left with 2 numbers on the outside, the green one. Okay. So people who said 3 got it right. There's lots of different ways to think about it. This is my favorite way to sort of do it quickly. Takes some getting used to. All right, those are rows and columns of M. Now let's talk about what does matrix M have to do with these direction vectors. So we're working on 36.2 here, sort of step by step. We're finding M, and I want to say, what does M have to do with the direction vectors d1 and d2? And I have a few different options for you. I got the rows of M are related to d1, d2. The columns of M are related to d1, d2. You can find something by doing a linear system, or maybe you think M has nothing to do with d1, d2. So those are your options. I'll give you a couple of minutes to work on that and think about it. Again, this is a sort of thinking about it question. There's no specific mathematical answer. It's how do you want to interpret the matrix multiplication to use it in this problem. Okay, let's see. Did anybody need more time here? Maybe that was too quick. It was almost too quick for me to finish writing what I wanted to write on the board. The two sort of options are you can think of the columns of the matrix, and then you get a linear combination of the columns, or you can think of the rows, and then you get dot products. Those are the sort of two possible things. Or you can set up as linear systems. Let's see what people think. Slight preference towards the columns. Linear systems, so it turns out basically everything in the course you can write as linear systems. And in this question, linear systems is a good answer, but it's going to be kind of a painful thing to do. So you can do this problem in terms of linear systems if you're a wizard at linear systems, but sort of conceptually speaking, it's going to be easier to think of it a different way. And I think you guys all voted for columns. What do columns have to do with things? So columns, we have linear combinations of the columns. What about the plane? What is a plane? The plane P. Let's go back to the question. How do you get the plane P? Somebody in the front row said it. Yeah, a plane is a set of all points which are linear combinations of the direction vectors. So it's a plane going through 0. All the points in the plane are linear combinations of the direction vectors. So the plane P is the points x, which are s times d1 plus t times d2, where s and t are parameters. Does that look more like columns or more like rows? Columns. So now the next question. Now you've seen this connection. We know we're thinking in terms of columns. I have some very suggestive things written on the board for you today to help you out. let's find the matrix M. So 36.2, tell me what M is. So I'll give you a minute to figure out what M is, and then I'm going to ask for it on top hat. Who thinks they know what M is? A few people. Who needs more time? A few people. Okay, we'll do another minute, and then I'm going to get some suggestions for what M could be. Okay, let's take a suggestion. Who can tell me what they have for M? So there are a few people who are ready near the front. Some people back there. Somebody back there have what M is? I thought I saw a hand. Maybe I didn't. Yeah.
M would just be a 3x2 matrix, whereas D1 and D2.
So you're gonna, M is a 3x2 matrix. We've already got that.
And the columns are D.
Three rows, 2 columns. So it's going to look like this. It's going to have sort of be rectangular. It's going to be taller than it is wide. 3 rows, 2 columns. And you're telling me I can just put D1 in for the left column, D2 in for the right column. Yeah.
Could M also be just zeros?
M could be all zeros. Yeah, that's right. Because if M is all zeros, then it will output always. The output will always be 0. If M is all zeros, then no matter what you multiply by, you get 0, and 0 is in the plane. So the solution you get sort of, it takes everything and smooshes it down to just the point 0, and 0 is in the plane, so that works. That's sort of a technically correct, but not fun answer. So I don't know. I don't know how to phrase that one. I guess that's the boring answer, right? It's always 0 is boring. What about this one? We've got D1 and D2, so when you write down linear combinations, if you multiply this by any thing, R1, R2, any vector R1, R2, you get R1, D1 plus R2, D2. R2, D2. Let's rename it to S and T. If we rename the entries of this vector to S and T, then it looks exactly like the formula for the plane. So if you pick the columns to be D1 and D2, this matrix is sort of exactly representing all the possible parametric form of that plane P, the vector form of the plane P. So there you go, that's a totally valid M. In this problem, you're actually given what D1 and D2 are, so you could write down what M is. Any questions or comments about that one? Yeah?
If we swap the columns, it still works, right?
Yeah, we can swap the columns and it would still work. So if you swap the columns, this will be S times D2 plus T times D1. That's totally fine. And in fact, remember planes, you can pick any direction vectors you want. So you can pick any matrix M as long as it had 2 valid direction vectors, you would get the whole plane out of there. So 0 is a direction vector for the plane, and that's why 0, 0 worked as an answer. Any direction vectors for the plane will work as an answer. If you want to get the full plane, you better pick 2 direction vectors that are allowed to go in the vector form. So if you remember, when you're picking direction vectors, if you pick 2 that are dependent or something, then you're not going to get the whole plane. Okay. Other questions or comments about that one? So let's look at the next part of this question is about finding a matrix K, and it also is talking about normal forms for the plane P. We got normal forms in another matrix K. It's going to have something to do with matrix multiplication. I think you might be able to guess what if you've been paying attention today. But I'm going to leave that one for you guys to do at home as well. So the matrix K, what does it have to do with the normal form for the plane P? How would you write it down? What should you think about? This is a really good exercise, and maybe we'll take up the answer quickly on Thursday's class. But for today, I'll give you guys a break, and we'll meet up again in, I guess at 2:10, I'll put up a top-hat question. If you come back at 2:15, you won't have missed any content. Okay, so we'll see you guys soon.